Hi guys, I'm Monica. I welcome you all to my channel Aerocar. So as we proceed further in our journey of aerodynamics, in this video we will be discussing about the topic velocity potential. So without any further delay, let's get started. Let us consider an irrotational flow. Now we know how is an irrotational flow defined, right? Irrotational flow is a flow where vorticity at each point is 0. Now if I have to depict that mathematically, or if I want to write that mathematically, how do I write that mathematically? We can write it as zeta is equal to curl of velocity is equal to 0. So this is the mathematical form how we can write the irrotational flow. Let us say this is our equation 1. Now what we are going to do over here is we are going to introduce a new term. Should I call it a new term or no? Or are we aware of this term earlier? Have we used this? Certainly not. So here we are going to consider the vector identity, that is velocity v, and we are going to consider this letter phi, which is a scalar function. So this scalar function we are going to consider. Now if I have to write this, so can I write v as something of this sort? Yes, that is, I will substitute this vector identity, that is our velocity vector, in terms of a scalar function. So how am I denoting this in mathematical form? If you look at this equation carefully, it is nothing but the curl of the gradient of a scalar function. That is what we can depict from this equation, and the curl of the gradient of a scalar function is equal to 0. So let us call this as our equation 2. Now if I combine equation 1 and 2, if we compare these two equations, as I said, we can write our velocity vector as gradient of phi. Correct? Let us say this is our equation 3. Now from equation 3, what we can see is that for an irrotational flow, we have a scalar function phi, and it exists as a gradient of phi. So I can denote my velocity vector as a gradient of a scalar function, which we have denoted as phi. Now this phi, what we are going to say is, this phi is called as the velocity potential. We name this term phi as a velocity potential. Now what is this velocity potential? It is a function of all the spatial coordinates, that is in terms of Cartesian coordinates. If I have to write, so phi will be a function of x, y and z, and if I have to write it in cylindrical coordinates, then it will be r, theta and z, or if it is the cylindrical coordinates, phi will be a function of r, theta and this thing. Now what we are going to do is, we are going to consider the definition of gradient. We are going to consider the definition of gradient in Cartesian coordinate form and our equation 3. So this definition of gradient definition, all of you might have come across your mathematics, and also in our previous lectures we have come across this. So can I write an equation in this form, that is ui cap vj cap and wk cap is equal to dou phi by dou x I cap, dou phi by dou y j cap, and dou phi by dou z k cap, right? So let us name this equation as equation 4. Now if we look at this equation, we have to say that the coefficients of the like vectors, that is the like unique vectors, must be the same, that is they are equal the coefficients of the like vectors. So which means I can write u as dou phi by dou x and v as dou phi by dou y, and w would be dou phi by dou z, right? So let us say this is our equation 5. Similarly, if we have to write for cylindrical and spherical coordinates, what will be our equations or the velocity terms? We will have Vr as dou phi by dou r. V theta would be 1 by r dou phi by dou theta, and Vz would be dou phi by dou z. Let us say this is our equation 6. And equation 7 would be in terms of the cylindrical coordinates. This I leave up to you as your homework to derive by yourself what will be the velocity terms if we are considering a cylindrical coordinate system. Spherical coordinate system. So this is in terms of the cylindrical coordinate system. So now if you observe carefully, when we look at this u, v and w and what we had studied previously, that is in our stream function psi, we had u is equal to dou psi by dou y and v is equal to minus dou psi by dou x. Certainly, if you people might remember, this is what we had derived when we were studying about our stream function. Now when we observe at these two terms, the velocity potential and the stream function, they seem analogous, right? Because in both the cases, what is happening is the derivatives, that is the derivative of psi and the derivative of phi, is giving me the velocity of the field in that particular direction. But hold on, are they actually analogous or do we have some differences? Yes, certainly we have some differences. What are those differences? Let us have a look. So the first difference between the velocity potential and the stream function is that in case of velocity potential, the flow velocities that we are obtaining are by differentiating phi in the same direction of the velocity. That is, u is equal to dou phi by dou x, and in case of v, that is differentiated with respect to y, and in w, it is differentiated with respect to z. Correct? But in case of stream function, it is vice versa. That is, velocity is differentiated to the normal direction. That is, the function psi, the stream function psi, is differentiated normal to the direction of the velocity. This is our prime difference. What is the second difference that we have? The velocity potential is defined only for irrotational flows. But in case of stream function, we can define it for both irrotational as well as rotational flows. The third difference that we have is of velocity potential applies to three-dimensional flows, whereas stream function, I can use it only for two-dimensional flows. Now, for two-dimensional flows, if we think of some examples where I can define this stream function, would be one example would be the axisymmetric flows that we have, that is flow over a cone. If it is flow over a cone, we have one example which has 0 degrees angle of attack. Correct? So one example is of that. And however, for such flows, what happens is only two spatial coordinates are needed to describe the flow field. That is in case of the stream function. Correct? Now, because I am saying that this velocity potential can be described by the irrotational flows, that is, velocity potential is used to define irrotational flows, we can also call them as potential flows. So we also name these flows as potential flows. Now, what is the relationship between these two? the stream function and the velocity potential, is there any possibility that we can establish a relation between these two? Yes, certainly we can establish a relation between these two. So in order to establish a relation, let us consider this as a line where phi is equal to constant. So this phi is our velocity potential and this line is a isoline. So because we say phi is equal to constant, let us name this line as an equipotential line because it is saying that my velocity potential is constant along this line. So I call this as an equipotential line. Now in space, if I draw a line such that gradient of phi is tangent at every point, the gradient of phi is tangent at every point. If I sketch such a line, which will also be perpendicular to this equipotential line, and this is my gradient line, so I can define this as a streamline, correct? Because it is also perpendicular to my equipotential line. And also we know one more thing, that velocity vector is equal to gradient of phi, right? We have derived this just a few moments ago. Now because this gradient line and isolines are perpendicular, we have seen this, or you might have seen this in mathematics when you are sketching a gradient Cartesian coordinate system, that is gradient of a scalar field in a Cartesian coordinate system. You will observe that gradient lines and isolines are perpendicular. That is, my equipotential line and streamline in this case are mutually perpendicular. Now in order to illustrate this mathematically and come to a conclusion that both these lines are actually perpendicular, how do we get the mathematical conclusion of this? The same thing as we had done in case of vector fields, we will take a Cartesian coordinate system and take equipotential lines. Let us say this is phi 1, phi 2 and phi 3. So these red lines indicate that phi 1, 2, 3 are constant along these lines in the Cartesian coordinate system. So here we consider a two-dimensional irrotational flow, and also the flow is incompressible, and this flow we are considering in the Cartesian coordinate system. Now these are my gradient lines, also known as the streamlines, as we have depicted over here. Now for a streamline, I know that I can write streamline psi of xy is equal to constant. When I say this, which means the differential of psi along the streamline is 0. So how can I write it mathematically? That is, the differential of psi along the streamline is 0. How can we depict that mathematically? Can I write it as dou psi by dou x dx plus dou psi by dou y dy is equal to 0, right? So let us say this is our equation 8. Now from our stream function, we know which is u and which is v, correct? If I substitute u and v, so this dou psi by dou x would be my v, where we have minus there, so here it will be minus v dx plus u dy equal to 0. So this is our equation 9. Now if we solve this equation for dy by dx, so when we solve these two equations, equation 9 for a dy by dx where psi is equal to constant, we get the equation dy by dx is equal to v by u, where this dy by dx is nothing but the slope of our streamline where psi is equal to constant. Now similarly for an equipotential line, I can write psi of xy is equal to constant. Following the same procedure, if I write d phi, which is dou phi by dou x into dx plus dou phi by dou y into dy is equal to 0. Now if I substitute or write this equation in terms of u and v, it would be u dx plus v dy is equal to 0. Let us say this is our equation 12, and if I solve this for dy by dx, where phi is equal to constant, dy by dx being the slope of my equipotential line would give me minus u by v. Correct. We have got the slope of the lines in both the terms where psi is equal to constant and where phi is equal to constant. Correct. If I combine these two equations, that is my equation 10 and equation 13, what is it that we get upon solving? We get dy by dx, psi is equal to constant, would be equal to negative of 1 upon dy by dx, phi is equal to constant. So this is the relation that we establish between the streamline and the equipotential line. Now what does this equation show? That is dy by dx psi is equal to constant is equal to negative of 1 upon dy by dx psi equal to constant. It shows that the slope of a streamline where psi is equal to constant, it is the negative reciprocal of the slope of the equipotential line where phi is equal to constant. So hence we mathematically prove that streamline and equipotential lines are mutually perpendicular. So this is it for this video, the relation between the streamlines and equipotential lines. In our further videos, we would be coming up with more such topics and some more derivations, and also we will be solving some of the problems. Thank you for listening. Stay tuned.